So Kai is a student of mine, and I'm very happy that he developed an algorithm, an application based on what I just presented, means the alignment of these two triangles. It's his application is based on. And so Kai, please present your presentation.
Okay, thank you. So hi everyone, my name is Kai Neumann, and today I'm presenting our contribution titled GAAlign, Robust Sampling-Based Point Cloud Registration using Geometric Algebra. So first of all, I want to start with a quick introduction to 3D projective geometric algebra, short PGA, which seems to be a common theme today. And you should already be familiar with that, for example, from the talk from Leo Dorst earlier today. After that, I introduce the problem of point cloud registration and then explain how our own method called GAAlign. After that, I'll then show what results we can produce with that and then end with a conclusion. Okay, first of all, what is 3D projective geometric algebra? Again, this is a type of geometric algebra which is especially well suited for dealing with 3D Euclidean geometry. And it consists of 4 blades of grade 1, which are E0 with squares to 0, and then E1, 2, and 3, which all square to 1. And we can use these 4 blades of grade 1 to then form blades of higher grades using the outer product. So for example, we can get E12 using the notation E1 wedge E2, where wedge is the outer product. And using this, we can obtain a total of 16 unique blades. And in this geometric algebra, any object can be defined as a combination of these 16 blades, so as a vector of 16 values. And for example, you can define points, lines, planes, etc. And what's especially interesting for our algorithm is that you also can represent rigid transformations, so rotations and transformations as using these blades. And these transformations are called motors. And they are formed on a basis that is shown here. It consists of the scalar, which is just the 1. Then we have 3 bivector parts that square to -1, then 3 bivector parts which square to 0, and then finally we have the quasi-scalar, I think, then the pseudoscalar. Then motors are equivalent to the exponential of a bivector, as Leo Dorst showed earlier. And the nice thing about bivectors is that the bivector space is linear, which is very good for interpolation. So if we want to linearly interpolate between 2 motors, we first have to take the logarithm, and then we can interpolate in bivector space, and then we have to take the exponential again to get back into the motor space. And this being said, as a fast approximation, which works quite nicely in practice, is that we can directly interpolate motors. So we just treat them as 16-dimensional vectors and then interpolate with these, between these. Okay, now I want to introduce the problem statement. Point cloud registration is a task where we have 2 or more point clouds with partially shared underlying geometry. So for example, we have 2 surfaces that share some parts, and we want to tightly align these surfaces. And so they have some overlapping parts. And the goal is to find a transformation that then aligns the overlapping parts with each other. So what's the state of the art for point cloud registration? There's been quite a lot of research in this topic. And the most commonly known and most popular algorithm is called ICP from Bessel and McKay from 1992. And there are also 2 well-known extensions of that. The first is called point-to-plane ICP, and then there's also symmetric point-to-plane ICP. And one of the still very well performing state-of-the-art analytical methods is called fast global registration from Zhu et al. From 2016. And this is in contrast to most of the newer publications, which are all machine learning based methods. And for example, those are NGENet or GAAlign. And in addition to the standard analytical methods and the machine learning methods, there are also some geometric algebra based methods. And most notably, the GAALMS algorithm from Lopez et al. From 2016. And this uses least mean squares adaptive filters to solve this problem of point cloud registration. Okay, now before I introduce our method, I just want to go on a quick tangent and introduce you to gradient descent if you don't know it already. This is a quite popular and intuitive minimization technique, which works in an iterative way. It takes a step in the direction of the negative gradient at each iteration. So on the left, we can see we start at a position x0 and we want to get to the minimum of this function fx. So in each step, we take a step into the direction of the negative gradient, which is shown here in red. And then we get to the next point, which is x1, x2, etc. And eventually we get to the minimum of this function. And it has a very simple update rule. So it's just xi plus 1 equals xi minus alpha times the gradient at the position xi. And the alpha here is a parameter that can be set freely. So to basically change a bit how the algorithm behaves. And this is called the step size, or also known as learning rate. One popular extension of this algorithm is called stochastic gradient descent. And this also works on large and noisy data sets. And it, for example, is popular in machine learning or derivatives of it. For this algorithm, for this extension, instead of just calculating one gradient, we choose n data entries that I named fk for each iteration, and then we calculate the average gradient based on them. So we always take a little step in the direction of the average gradient. And the update rule is it's very simple to the previous to the one on the previous slide. Here we just have instead of just calculating one gradient, we're calculating n gradients, and then we're dividing by n. Okay, so why did I just explain this to you? This is because the idea of GAAlign is based on stochastic gradient descent, because we thought, what if we do the same thing? So this iterative step-by-step getting closer to a minimum, but instead of using gradients, we're using motors. Okay, so now let's introduce it a bit further. GAAlign, as I just said, uses the algorithmic structure of a gradient descent. And as the input, we use a source point cloud and a target point cloud. Usually the target point cloud is the one that stays fixed, and we're trying to move the source point cloud onto the target point cloud to get a tight alignment. And in addition to that, we also use a set of correspondences as input. So these are points that we assume are the same surface points. So these are the points that need to be aligned onto each other. And these correspondences can be calculated using a number of ways. For example, using feature-based methods, or simply using, for example, taking the point that is closest in the other point cloud. And as the output, we are calculating a motor, so a rigid transformation. And as Dietmar already said, this algorithm uses PGA-based motor estimation at its core. And this is from a guided tour to the plane-based geometric algebra, PGA by Dawson Mechanic. And we implemented this using GAAlign, so the geometric algebra algorithm optimizer that Dietmar just presented. And we specifically extended GAAlign to support the previously unsupported 3D PGA. Okay, now let's explain the algorithm a bit more in detail. As I said, it's an iterative algorithm with the same structure as a gradient descent. So we are trying to get closer to the goal step by step. And in each iteration, we are estimating a number of motors. In this case, we called this number n triangle. So we are trying to estimate n triangle motors. And each motor is calculated from a set of 3 random correspondences, which is basically the same as taking one triangle from the source point cloud and taking another random triangle, and then we map these onto each other. And we are using this motor estimation that Dietmar showed to then estimate the motor from these correspondences. After that, we sum the motors and then we normalize them. And summing and normalizing is basically the same as calculating an average motor. And then, as a third step, we scale the resulting motor, so the normalized motor, by the step size. We cannot simply multiply it by alpha, but we need to interpolate between our motor and the identity motor, so which is no movement or rotation at all. And in PGA, this is just the scalar, so just 1. And so we interpolate between 1 and our new motor. And then we apply our new motor, so the resulting scaled motor, to the source point cloud. So we move our source point cloud a step towards the target point cloud. So in the next iteration, when we are calculating new motors, we're calculating from the updated positions. Okay, and finally, we're then joining the new motor with the output motor, so we get a full, complete transformation in the end. Okay, now I've explained everything in detail, but the main part, motor estimation. And as I said, and as Dietmar already promised, this is the motor estimation from triangles algorithm from a guided tour to the plane-based geometric algebra by Doss and Decanic. And this works in 4 steps, which are visualized here. So we have 2 triangles, A1, B1, C1, and A2, B2, C2. And we first move A1, so this one corner, onto A2. Then we are rotating the one line L1 onto L2. And then finally, we are rotating the whole plane P1 onto P2, which then gives us the full transformation. And in each step, we are using these basically the same equation with just different objects. So it's always 1 plus A1 by A2, or 1 plus L1 divided by L2. And we are always dividing by the same term again, so we get the normalized motor. Yeah. Okay, now I've explained how our algorithm works. Then I want to show you what it can do. First of all, we used synthetic test data. And for this, we used 4 different models. And we used the same source test approach for testing. So we always use the same model and try to align it to itself. But instead of just using the pure models, which would be a bit too easy, we first of all, we used randomized transformations. So we moved them away from each other and rotated them. Then we disturbed both point clouds, either with Gaussian noise or outliers, to also test the robustness. And then finally, we also dynamically cut them to have a specific overlap, which can range between 20 and 100%, just to make it a bit harder. Okay, and the first test that we did was to see how robust we are against noise. So we disturbed our models with Gaussian noise, and then we measured the registration error over an increasing noise strength. So here on the x-axis, we have the noise strength. On the y-axis, we have the root mean square error, which is basically just the alignment error. And what we can see here, for comparison, in blue, we have our algorithm, and then we have 3 ICP variants, all implemented in the PCL library, so the point cloud library. And then we also compare ourselves against the geometric algebra-based method GAALMS. We're using two versions of it. First, the basis version, and then I think 1 year later, they published an updated version, which uses a steepest descent approach. And we also use that. And what we can see here in the graph is that our algorithm performs very close to the best algorithms. So it has a high robustness against noise. And it's also notable that the point-to-point variant, so the very basic ICP variant, and the GAALMS with the steepest descent variant produce exactly the same results. Okay, we then as a second test, we tested the robustness against outliers. And on the x-axis, we can see the outlier percentage. And then again, we measured the alignment error. And what we can see here is that GAAlign is much more robust than other algorithms against outliers. Okay, in addition to the robustness test, we also compared the runtime performance. And here we tested over an increasing number of correspondences. So basically how large the input point clouds can be against then the runtime. And on the y-axis, we can see the runtime in milliseconds. And what's notable here is that the runtime of our algorithm stays constant over the number of correspondences, while the other algorithms all scale approximately linearly. This is also true for the GAALMS steepest descent, which is located here very near to the y-axis, which just has a very steep, which is just very steep, but it's also basically linear. Okay, and then as a final test, we tested the performance in a real-world pipeline. And for this, this means that we used it in combination with a 3D key point detection. So we used FBFH features. And we did 100 repetitions per model. And we randomly rotated and translated the input point clouds. And we also randomized the overlap between 20% and 100%. And the metric that we use to compare our algorithm against other algorithms is the so-called alpha recall, which is just a fraction of tests with an error smaller than a specific or a variable threshold alpha. Okay, so these are the results from our real tests. Now we compare ourselves against quite a few more algorithms. And on the left, we have the plot, we have the results for tests without noise, and on the right, we disturb the point clouds with noise. And in these types of plots, so always on the x-axis, we have the threshold alpha, and on the y-axis, we have then this alpha recall, which is just the fraction of tests which are smaller than this threshold alpha. And what we can see here in the, so for these types of plots, up and left is better. And what we can see here for tests without noise, our algorithm outperforms all other tested algorithms. And in an environment with noise, we can see that it's very close to the best other algorithm, which in this case is FGR, so fast global registration, which is this analytical method. And also notably the neural networks, so NGENet and GAAlign, which are state-of-the-art on common benchmark sets, did not really perform well in my tests. Okay, so in conclusion, we presented an original geometric algebra-based algorithm called GAAlign. We implemented this using GAALog, which was specifically extended to support the 3D PGA. Then we tested the robustness, and we see that our algorithm is very robust against noise and outliers, and most specifically against outliers, and that we also have an improved scalability. And finally, in a real-world pipeline together with a feature detector, we achieve a state-of-the-art accuracy. So thanks for listening. And if you want, you can try GAAlign and GAALog for yourself. And GAAlign is also open source, so you can use the QR codes or the links provided below. Thank you.
Thank you very much, Kai. Are there any questions? Yes.
Hi, this is Leo Dorst. Thanks for reading what you wrote. The algorithm you used for aligning the triangles was meant as an example of when the triangles are actually exactly deformed by a motor.
Yes.
So use it in a noisy case. Do you have a feeling for what it estimates then as alignment and why it is apparently?
Yeah, so if the triangles aren't exactly perfectly the same size or just perfectly transformed, which can happen if the correspondences are noisy, etc., then the alignment is not perfect. So it generally goes in the correct direction, but we don't get an exact matching transformation. So the transformation isn't like a perfect alignment, which is why it's so beneficial for us to use it in this robust loop, where we just sample correspondences and calculate a number of motors and then average them, and just take a step into in the direction of the alignment, so in the direction of the motor. So even if each motor isn't perfect on its own, the summed and averaged motors generally go into the correct direction, which works quite well in practice.
The next question is by Ellen.
So gradient descent is well known to be subject to problems with local minima, getting to local minima. But having said that, your performance results are quite impressive. So is it the nature of the problem you're solving? Is it in some secret sauce in your algorithm? Or, why does it seem that that doesn't stand as a problem for you?
Well, about the local minima, I think it's based on how the problem is defined. In developing this method, I also tried extensions like the Adam optimizer or other algorithms that basically extend this gradient descent method a bit more and make it more robust. It didn't really benefit for me, and I decided for the simplicity of the gradient descent approach. And for me, I think it's the type how the problem is defined that it works quite well. So for point cloud registration, there aren't really local minima which you can get trapped in if the correspondences are good enough. So I think that's not a problem that we face here. I hope that answered your question.
Hello. Hi, here's Wilder Lopez.
Hi.
I wrote
Hi.
the GAALMS.
Yeah. Hi.
Hi. So it was great work. So I was interested to see, have you tried this in any embedded devices? Because it would be great to see this performance on low power devices.
Oh, no, I haven't yet. No. Right now it's C++ based, and I tried it on my home PC, and but it would be interesting to test it on an embedded device.
Right.
What I'm using is for the triangle interpolation part, where I'm calculating all these motors in parallel. All these motors. This is highly parallelized, so I'm just doing as many as I can in parallel. So maybe that doesn't translate very well onto embedded devices. But it would be very interesting.
Right. I will have a look at your GitHub. I have it here.
Yeah.
I put myself to deploy on something embedded.
Yeah. If let me know what comes out of that. That would be very interesting.
All right. Thanks. Great work.
Yeah. Thank you.
Okay. The last question will be by Joan now.
Hi, Kai. Thank you. Really interesting. It's Joan Lazy. So what happened? Have you tried some sort of algorithm, adaptation of your algorithm where you don't need the feature matching? So you can guess, because, a lot of the things you're comparing it to don't need correspondences. They work out.
Yeah. Well, they take they estimated correspondences themselves, mostly not feature based, but for example, the standard ICP variant is just distance based, so it takes the closest point and then tries to move into that direction. This is also possible in my code, and I tested that. It depends on how far the point clouds are off. So ICP fails if the point clouds are off by more than a few degrees or a few centimeters, depending on your size. So this feature-based approach is much more robust because they can be more out of sync. So they can be farther away from each other. But I've also implemented a simple distance-based correspondence algorithm, and that also works quite well.
Okay, that would be interesting to see, because you often get 2 point clouds from different cameras where there are no obvious features and no correspondences, no true correspondences. So addition.
Okay, yeah.
Okay, thanks.
Yeah, thanks.
Yeah, thanks. Oh, we have an additional question.
Great talk. My question is, I'm familiar with Ransack. If you're not familiar with Ransack, you choose a transformation. Yeah. You see how many correspondences are within a threshold distance. It tends to be very robust to outliers. And it seems when you're choosing random subsets, you're going to include a lot of motors in your composition that are terribly wrong. Is there anything to prevent that? Like when you're choosing these random subsets, is there some intuitive way to understand why I'd want to include all those motors into the composition?
So yeah, that's a good idea to use Ransack to estimate, to be more robust against that. For me, in my test, it just proved that, so I've seen that if I take enough motors, most of them aren't terribly wrong. So if fewer of them are terribly wrong, then I take a slight step into the wrong direction. But based on this iterative step-based approach, mostly it's wisdom of the crowd. So most motors are correct. If we are dealing with much noisier correspondences, then something like Ransack would be a good idea, I think. But for me, it's just this iterative. So the averaging proved to work very well in practice.
Hi, Kai. This is Eric Wieser, and I've got a question about point 2 on that slide. In particular, you normalize the motor, but your motor might be on the motor manifold. So your motors start off with 6 degrees of freedom, but their coefficients have 8. And when you normalize the motor,
yes.
So how do you get rid of the extra degree of freedom? So
as far as I understand it, the normalizing brings it back to the manifold. So summing the motors, the motor that we get from just summing them doesn't have to be a motor on the motor manifold. Normalizing, I think it recovers 1 degree of freedom. You're right. I think it's not exactly by definition a true motor in that case. In practice, it works very well. That's what I can say. But you're right. I don't think that we do anything to basically make sure that it's per definition a correct motor.
Great, thank you.